Welcome friends and welcome to my series of video lectures on design of RCC structures. We are studying chapter 1 fundamentals of reinforced concrete. In that this is video lecture RCC 1.4 properties of concrete and steel. For best video quality, watch this video lecture on a laptop or a desktop with resolution set to 1080p HD. Expected learning outcomes from this video lecture are 1. To draw and interpret stress-strain curve of concrete. Second, to explain grades of concrete and steel used in RCC. Third, to draw stress-strain curve for reinforcement steel. The contents of this video lecture are 1. Properties of concrete. Second, properties of steel. We are going to use some key terms in this video lecture: characteristic strength, design strength, partial safety factors, rebars, IS 1786-2008, HYSD steel, TOR steel, CTD steel, TMT steel. Friends, before we begin, here is Smarty for us with some tips. Write down your own notes while watching this video. Pause or rewind the video whenever required. Do solve the formatting and summative assessment quizzes provided in the video. Friends, in this part of video, we are going to study the properties of concrete. We have already studied the subject of concrete technology earlier. So let us just have a brief revision of the important points of the concrete technology. Concrete is defined as a construction material made up of a mixture of cement, fine aggregate, coarse aggregate with water and admixtures. There is a term called concrete mixed design, which is very important in relation to concrete. So, concrete mixed design is the procedure of deciding relative proportion of quantities of these 5 ingredients. So, from the definition of concrete, we make it clear that concrete is a mixture of 5 ingredients: cement, fine aggregate, coarse aggregate, water and admixtures. Now, what is to be the relative proportion of the quantities of these 5 ingredients? That is decided by the systematic method of what we call as concrete mixed design. So with this we get different combinations, we get different configurations of the relative proportion of quantities of these 5 ingredients, and this gives rise to what we call as grades of concrete. So what is grade of concrete? Grade of concrete represents a specific proportion of quantities of ingredients of a concrete variety. Now, every concrete is designated as concrete grade MFCK. You can see this symbol, capital M, and after that we put the value FCK. For example, M15, M20. So a concrete is designated as M15 grade concrete, M20 grade concrete. Here the letter M means mix, and this figure which comes after that, say 15, 20, that is FCK, that is the characteristic strength of that particular concrete, which is 28 days characteristic compressive cube strength of the concrete expressed in megapascals, that is in Newton per mm square. So here we come across the term characteristic strength. In my earlier video, I have explained in great detail the concept of and the meaning of characteristic strength. So as IS 456 defines it, characteristic strength is defined as the strength of material below which not more than 5% of test results are expected to fall after testing. That is, this is the value of strength below which 5% test results may fall. So This is the idea of characteristic strength. So M20, M15, in that 20 or 15 is FCK, that is characteristic strength. Now, there are various grades of concrete available. We can prepare concrete of various grades. Out of that, IS 456 2000 is recommending in table 5, it's table 5, that you must use minimum M20 grade of concrete. You must use minimum M20 grade of concrete in case of RCC structures. So there are other grades also. It starts from M7.5, M10, M15. So these are the grades lower than M20. These grades cannot be used for reinforced concrete. They can be used as plain cement concrete PCC, where we want to lay PCC layer under an RCC component. So there we can use those concretes of grades lower than M20. But for RCC work, for reinforced concrete work, we have to use minimum M20 grade of concrete. So in short, we can say minimum grade of concrete is M20. Here M stands for mix and 20 is FCK in Newton per mm square for that concrete. Friends, now we proceed for the very important aspect of the properties of any material. So for concrete also, that is the stress strain curve of concrete. Stress strain curve of concrete. So stress strain relationship of concrete. This is as given in figure 21 of IS 456 2000. The IS 456 2000 has standardized the stress strain relationship of concrete. Now let us understand this stress strain graph or the stress strain curve or stress strain relationship of concrete in a greater detail. We are going to require all the numerical values and the shape parameters of this curve every now and then in the topics which we are going to study ahead. So pay attention carefully and understand the stress strain curve of concrete. Now, first of all, here we see that on the x-axis we are plotting strain, which we are denoting by the letter epsilon, whereas on y-axis we are plotting stresses and we are denoting them by small f, letter small f. Now let us see the curve. Okay, before we proceed for the shape of the curve, let us see what is plotted on the axis, x and y axis, or strain and stress axis. Look at the strain axis. The strain axis starts from 0 and we have got values 0.001, 0.002, 0.003 and there is a value 0.0035. So it is halfway between 0.003 and 0.004, which may come ahead. So this is the last value of strain on the strain axis, 0.0035, and we are calling here that value as epsilon Cu. Epsilon Cu. This is the symbol used by Iscode itself, and the meaning of this symbol is epsilon for strain, C for concrete, and U for ultimate. So later on we are going to see in the assumptions for limit state design that this is the highest possible permitted value of strain in concrete by the Iscode. So Iscode is saying that you can assume that concrete has broken or it has collapsed if the strain value of concrete is 0.0035. So for numerical calculations, we cannot experimentally we can observe a collapse, a crushing, but we can see physical cracks. That is on the experimental side. But on the in the design side, we cannot go for all these symptoms, but we have to go for the numerical value which will mean that the concrete has cracked or collapsed. So that value of epsilon Cu is 0.0035 for concrete, and we have to note one more point that this epsilon Cu 0.0035 is the value for any grade of concrete. It does not depend on the grade of concrete. That means for M20, M25, M30, M35, all the concretes will have same value of strain for as the maximum value, that is 0.0035. So while plotting the graph, we have to first of all note down this axis. Now on y-axis we get the FCK, the stress. The highest value of stress, as we know, is FCK. That is the 28 days cube strength, crushing strength of a cube, as we know. So this is FCK. So if it is M20, this FCK here you will put the number 20. Okay. So if it is M20 grade concrete, this FCK is 20. Now let us look at the shape of the graph. We see three graphs here. Let us see the topmost graph first, because that is the graph which we will get from the experiment, or we will get from this compression testing machine. You can see that there is a huge heap of concrete cubes. This concrete cube is a representative concrete cube. You can see its dimensions as 150 mm by 150 mm and by 150 mm. We test this in this compression testing machine and we get the value FCK finally. After having tested so many cubes, finally we calculate the value of FCK from it. And if we plot the graph, in that case, while testing the cubes, if we plot the graph of strain versus stress, we get this shape. Now let us understand this shape. This shape is having two parts. First part is a parabolic part which is up to 0.002 strain. This is a parabolic part. And after that it is a straight line part. So from 002 to the final last value 0.0035 epsilon Cu, this is a horizontal straight line. So this is what is an idealized curve given by the IS 456. Now here we are saying curve for characteristic strength. So this is the curve for FCK. Here we can see the cube being tested. So this is the actual real curve for characteristic strength. Now we know that in the earlier video again we have seen that while testing a material, we have to handle certain uncertainties and we have to anticipate so many things. And because of that, we have to apply what we call as partial safety factors to the values which we have obtained directly from experiments. That is why what IS 456 is telling us is we have to reduce this value FCK twice. We have to reduce it first because we are testing it for cube in the UTM, I mean the compression testing machine, and we are actually applying it to a structure. So here we are deviating the situation of testing and situation in which the concrete is actually subjected to forces. These two situations are different. So whatever we test and find out for a cube in the compression testing machine, that cube, this concrete is not behaving as a cube in the structure. So it is behaving differently in the structure. So we have to distinguish between cube strength and the strength that is expected in the structure. So Iscode is saying even if your cube gives FCK, you reduce it to 0.67 FCK. So Iscode is giving a second value of that stress to reduced. That is, you can see that this, if you just calculate, it will become a factor, partial safety factor of 1.5. So Iscode is saying you reduce this FCK by a factor by 1.5, so that this becomes 0.67 FCK. So here we are taking cognizance of the fact that we are testing it as a cube and we are using it in a concrete, in a structure, and that is why we are reducing the strength to 0.67 FCK. But this was one change, one difference. But there are other uncertainties about testing which are usual, and that is why Iscode is saying though you have reduced it to 0.67, you have to further reduce it by a partial safety factor gamma m equal to 1.5. I think we have given a detailed consideration to the factors of safety and all that in my earlier video. So I will simply mention that we are using two factors of safety at a time to concrete as per IS 456-2000, and those are 1.5 to reduce it from cube to the structure, and secondly to reduce it further to design curve as again 1.5. So if you divide this FCK twice by 1.5 and 1.5, you will get a value 0.446 FCK. So 0.446 FCK. So this is the value of our use in design. So you will notice here that the actual FCK is getting reduced to 0.446 FCK. That is only 44.6% of the original strength of concrete is actually used when we are designing a structure. You can understand this large factor of safety, the importance and the need of this large factor of safety because of the complicated nature of production of concrete as well as of behavior of concrete under load, and that is why we reduce the value to that extent. So we can say that the design strength FD, design strength, is the strength equal to 0.446 FCK for concrete. Now we get this second curve for concrete in structure and we get this third curve for the design strength. So we can say that this lowermost curve, parabola up to 0.002 in all the three cases and straight line thereafter. So this lowest curve is what we call as design curve, and that highest curve is the actual real curve. So from the design point of view, from the calculations point of view, for us the stress strain graph of concrete is only this much, only up to the design curve for the purpose of. So here we have seen the person is doing some design. So these are the three steps where we drop the strength of concrete. So this was in brief the introduction to the stress strain relationship for concrete. We can see here that if we look at these figures of strain, there is a little coincidence. If you recollect, in steel structures or for the stress strain graph of structural steel, there is again a strain value of 0.002. Actually steel and concrete are not directly dependent on each other in their properties. They are having, obviously they are independent materials, so they are having independent properties. But there seems to be a coincidence about this value 0.002. We find that the value 0.002 is the value in stress strain curve of steel, where the graph deviates from straight line to a minor curvature and then further plastic area and on so on. So that is the point of 0.002 value for steel. Here coincidentally, here the parabolic shape is up to 0.002 for concrete also, and that is why this 0.002 value also seems to have some significance. Now if we divide this part, the parabolic part becomes 4/7 and this becomes 3/7. So 4/7 part of this concrete curve is a parabola and 3/7 part is a straight line. So we say that this concrete block or concrete stress block, as we are going to call it later on, this concrete stress block is a parabolic rectangular shape. Now IS 456-2000 is allowing us to have our own experimentation and have our own curves also. But it is obvious that no one will go for this rigorous exercise and go for having their own curves. So it is better to presume, and it is usually done in the practice, that we presume this stress strain curve. Now we know that the properties of a material, one of the properties is Young's modulus. Young's modulus is the, as we have seen in case of steel also, Young's modulus can be calculated from the stress strain graph as the slope or the straight line portion of the graph. Now here we find that the graph starts directly from parabola. There is no straight line portion in the graph at all. So we will say that there will be a variable modulus of elasticity, because you will have to draw tangents at every point to this parabola and find out that slope. So this is where concrete creates a little problem, theoretical problem for us. So here Iscode comes for our help, and Iscode is saying that you can take the short-term elastic modulus of concrete as EC. E is Young's modulus of elasticity, capital E. C for concrete, as 5000 root FCK. 5000 root FCK. So what Iscode has done is Iscode has expressed that Young's modulus. Instead of going into drawing tangents and all that, Iscode has simplified it by giving us a formula EC equal to 5000 root FCK. Now there is second thing also. We know that concrete is weak in tension, but it doesn't mean that it doesn't have any tensile strength at all. It does have some tensile strength which is poor, but which is there. So sometimes while dealing with the cracking of concrete and all, we are required to consider the tensile strength of concrete also. But we know that it is impossible to test concrete for tension. Just as we test it for compression, it is not possible to test it for tension. So the Iscode is giving us one more formula, that is tensile strength of concrete may be taken as its flexural strength, and that formula as gives is FCR. FCR means the flexural strength of concrete, which is to be taken as, which you can take as 0.7 root FCK, square root of FCK. So Iscode has made this FCK as the indirect measure of measurement of EC as well as FCR. So these are the two values given by the Iscode, and we can use them whenever required. So in this part of the video lecture, we have seen, starting from the definition of concrete, the different grades of concrete. The minimum grade is M20, then the stress strain graph in detail, and finally the elastic modulus and tensile strength of concrete. Friends, after having studied the stress strain graph of concrete and properties of concrete in the earlier part of this lecture, we will proceed for the properties of reinforcement steel. The reinforcement steel is also called as a rebar, as we know. Now let us enter into the world of steel, reinforcement steel. Now here we see a table in which three types of rebars are shown. So we can have three types of rebars as allowed by IS 456-2000. So first is mild steel plain rebars, second is high yield strength deformed HYSD rebars, and third is thermomechanically treated, that is TMT rebars. Now just having a glance at this column itself tells us that the first and second, they are now obsolete. Iscode has permitted them, but in the market, if you consider, since there are advancements going on in steel industry very rapidly, since last 10-15 years, we are commonly using the TMT bars as the reinforcement or rebars. So these mild steel plain rebars and high yield strength deformed HYSD rebars, they are becoming obsolete. They are not much used, and that is why we will not concentrate much on them. But as a matter of history and as a matter of the information given in IS 456-2000, so far as IS 456 has kept it in the code, IS 456 has not removed it from the code, I think it is better that we should know something about it, but we will not focus much on that. So let us quickly go with the mild steel plain rebars. Okay, so the reinforcement, this reinforcement also comes in two forms: cold worked mild steel bars and hot rolled mild steel bars. You know that steel is manufactured from the iron ore, and it is molten at a very high temperature, say 17 degrees Fahrenheit, and it is undergone with so many metallurgical processes. The carbon and manganese are the elements involved in giving the yield strength and all those things about the metallurgy of steel. So the cold worked mild steel bars and hot rolled mild steel bars are the two varieties of mild steel. Now the description: a mild steel bar is having plain surface. It doesn't have grooves, like you can see in this diagram there are grooves. So these grooves are absent for mild, so it is called as plain surface bar. Now it has got less tensile strength. In RCC, according to IS 456, we call this as FE 250 grade bar. FE 250. The 250 is the characteristic strength of that steel, which is also the yield strength of the steel. So that is, the strength is 250. As compared to that, we can see that the strength of these Tor steel bars are FE 415 and 500, and now we have gone even up to FE 600 with TMT steel. So this 250 is much less strength, but it has got good ductility, as uh, the metallurgical process is like that. But now that ductility point is also taken care in the TMT steel, and that is why the description of this bar is just a part of a remembrance, that's all. Now the IS codes used for IS 432 and IS 1139 part 1, part 2 and so on for the mild steel. Now secondly, the HYSD steel bars, rebars, they are advanced than the mild steel. The purpose of providing these bars was to increase the strength. So that Fe 250 was increased to Fe 415 and Fe 500. They are cold twisted deformed, that is CTD bars, commonly called as cold twisted deformed bars, or cold worked deformed bars also they are called, cold work deformed bars also. So, and there are some hot rolled deformed bars also. So these are the two varieties that come in these high yield strength. So high yield strength is the self-explanatory term, that you will get better yield strength, and they are deformed bars. They are artificially deformed or twisted. So this is what we get, so these grooves you get. So they are also called as Tor steel bars, TOR. If you meet some engineer, say who worked as 15 to 20 years back, he will say that this Tor steel was very common in those days. It was an advanced steel in those days as compared to mild steel. So that Tor steel is a brand name. That is Touristic Steel Corporation of Luxembourg. So this industry steel corporation, they produce these bars and popularize these bars to a great in a great measure and magnitude. So these bars were called as Tor bars. They are actually CTD bars. So IS 1786 2008 gives the details of these bars. Now we come to the last, which is the important point, type of steel for us. This is thermomechanically treated, that is TMT rebars. These are commonly used. Now what are the grades? Now whenever we will be doing the design hereafter in RCC, we will be using all these grades of steel. So this is just as we have got M20, M25 concrete and so on, we have got steel grades as Fe415, Fe415D, just note it, Fe415S, Fe500, Fe500D, Fe500S, Fe550, Fe550D and even Fe600. Now IS 1786 2008, along with its amendment 1 in November 2012, and IS 456 2000, they are together mentioning these grades of steel. Now this Fe600 is yet to come in the course, but it has come in the market. So in this, the D, Fe415D, then Fe500D, this letter D represents ductility. So this Fe415 and Fe415D, what is the difference? So Fe415D is having all the other strength properties same, but this Fe415D is more ductile, so the ductility is more. So this is another variety, you can see. So here you can see TMT rebars of 12-meter bundles stacked on a side. So the TMT rebars from the market, they come as in the form of 12-meter bundles. They are grooved on their own surfaces. Now let us see what are the advantages over the earlier prevalent steel, or the Tor steel, or the CTD steel. So first is higher strength varieties are available. Fe550 and Fe600 are available. Second thing is high ductility. The CTD steel suffers a drawback that it is not as ductile as mild steel, but that drawback is removed by the TMT steel by having a high ductility. If you go sometime into the details of the manufacture of the metallurgical processes that the TMT steel undergoes, you will realize that it is having high strength but high ductility also. The third thing is it has got high corrosion resistance. This is also a great advantage over Tor steel and mild steel. Both of the earlier steels were having this drawback of high corrosion susceptibility, but now the TMT steel is having high corrosion resistance, no residual stresses. In the cold twisted bars, CTD, cold deform or twisted bars, the process of twisting was inducing some stresses in the bars which were remaining as residual stresses throughout the life of the bar. So that was a sort of disadvantage for the CTD bars. So that is removed here. These grooves are not made by twisting the bars, and that is why no residual stresses are there. There is good bond because again of the grooves on the TMT bars. We know that in RCC, concrete and steel will work together as a composite material only if there is a perfect bond between concrete and steel. That bond of concrete, steel with concrete, will be strengthened by these grooves that will resist the slip between concrete and steel. So these are the advantages of TMT steel over Tor steel. Now IS 1786 2008 provides the provisions for this type of steel also. Now what are the common diameters which are available? It starts from 4 mm diameter. 4 mm diameter bars were not available in Tor steel or even mild steel. It used to start with 8 mm for Tor steel and 6 mm for mild steel. But now we can have 4, 5, 6, 8, 10, 12, 16, 20, 25, 28, 32, 36, 40, 45 and 50. This 40, 45, 50, these three diameters were not available in the earlier steels. It used to end only up to 36 mm maximum size. So these bar diameters, this is a big variety of bar diameter available in the TMT bars. There is one more advantage that due to its means commendable ductility, you can get now the coil form bars also from 6 mm to 12 mm range. So if you want 6 mm to 12 mm bars, you can get them in the form of these coils also. You can uncoil them using a machine and then you can use them on site. So there are some benefits: nominal wastage at working sites, no overlapping required because this bundle is quite long. You can see here, if you get a 6 mm 1 metric ton bundle, it is 4505 meters long, 4505 meters long. 12 mm diameter bundle, 1000, that is 1 kilometer long, you can say 1126 meters long, whereas you get this only 12 meter bundles on the site. When they are in straight form, they can be coiled like this. So this is a good advantage taken from the ductility of the TMT bars. So no overlapping required because you would get long length easily. Increase in work efficiency, money and time saving was there, but there is a disadvantage that they require special machines to work with because they are required to be straightened. So that is why this sort of disadvantage also there. So as an information, we should know that the bars, TMT bars from 6 to 12 mm range, they are also available in coil forms. So this was a brief overview of the properties of reinforcement steel. Only one property remains that we will see in the next slide. So friends, in continuation with the properties of reinforcement steel, we will see stress-strain relationship for steel. Now we have IS 456 has given two broad varieties of steel. One which is steel bar with definite yield point. Definite yield point. So these are mild steel or grade Fe 250 bars. Right now we have seen that table in which the first variety was mild steel or plain bars or grade Fe250 bars. As I told you, they are no more used, they are obsolete, but Iscode is giving in figure 23b of Iscode page 70, this graph, representative stress strain graph is given. Here you can see there is a definite yield point. There is almost a straight line here and another straight line here. This curvature is almost negligible. That is why we can say that this is a definite yield point. Only ductile materials or ductile steels can have this type of yield point. Now, what Iscode is saying, this is a strain axis, this is stress axis. This graph is quite simple, that there is a straight line like this and a horizontal straight line like this. So this is Fy, this is characteristic strength, and this Fy is reduced by 1.15 factor of safety. So this factor of safety as compared to concrete, this total value will amount to 0.87 Fy. So this value will be 0.87 Fy as compared to concrete, which was 0.0446 FCK. This is 0.87 Fy. So this lower factor of safety is provided by the Iscode for the steel. So this was about the mild steel. Now the second, which is our TMT steel or the tar steel. So Iscode is providing this type of stress strain graph. Cold work deform bar, that is the CTD bar which we said last time in the last slide, tar steel bar. So this will be of this form. Here you see that there is, similar to this graph, there is a straight line portion. So it is having a straight line relationship because it is steel, but that straight line is getting deviated by a curve for a considerable length, and then it is becoming horizontal. So this enlarged curvature and this negligible curvature, this is the only difference between the two stress strain graphs. Now, because this curvature is like this, if your strain falls within this curved region, what will be the value of stress that you will take? So these intermediate points Iscode has plotted, and it has given it as 0.8 Fy, 0.85 Fy, 0.90 Fy, 0.95 Fy, and 0.975 Fy, and finally it is Fy. So this is the graph. So this Fy is the characteristic strength graph, and this Fy upon 1.15 is the design strength graph. This is the design strength of steel for calculation purpose. So just as we had got Fd for concrete, here this is Fd for steel. It is Fy upon 1.15, which will amount to 0.87 Fy. So if you need some intermediate values for 0.001 strain, so all these strain values and the stress values, they are given. So here we find this 0.002 critical value at this straight line portion starts. So this is the stress strength graph for tar steel, or even we can use it for the TMT steel also. And because these intermediate values may not be taken from the graph easily, Iscode is also giving, in fact SP16 is giving this table in which salient points on the design stress strain curve of cold work deform bars are given. Salient points means these important points during the over the curved part. So these are the values of stresses. So whatever values of stresses are given here, the same are given here. Some intermediate values are also given, and they are saying that if you want still intermediate value, then you can do the linear interpolation. So by linear interpolation, so this is just an additional facility provided by the Iscode. So friends, I think we have given enough consideration to the properties of steel also in terms of stress strain relationship. Now before we close the video lecture, we will have a formative evaluation quiz, a self-test. So pause the video and write down on a question paper, the answers of the following questions. First is, draw and describe stress strain curve of concrete and the related terms. And the second is, draw and describe stress strain curve of steel in both the varieties and the related terms. So do means perform this exercise and then continue for the video. So now we come to the conclusion of this video, summing up. This was lecture 1.4 in chapter 1. So properties of concrete and steel. We started with expecting some learning outcomes from this video lecture. They were as 1. To draw and interpret stress strength curve for concrete. To explain grades of concrete and steel used in RCC. And third, to draw stress strength curve for reinforcement steel. So the contents of this video lecture were 1. Properties of concrete, 2. Properties of steel. We also used some key terms: characteristic strength, design strength, partial safety factors, rebars, IS 1786-2008, HYSD, that is high yield strength deformed steel, TOR steel, CTD steel, cold twisted deformed steel, TMT thermomechanically treated steel. So these were the key terms we used. If you recollect and you just ponder over these terms in your mind, it will be easy to recollect the content of the lecture. You have to contact your teacher for any doubts or queries you have. Summative assessment quiz will be there. So as usual, I will be giving you the Google quiz of 40 marks, that is 20 questions on this video lecture. So do attempt the online summative assessment quiz provided by the teacher. I will be providing the link at the bottom of the description in the YouTube for this video. So do attempt that quiz. So now it's time to say goodbye. So our best friend Smarty is back with us, saying us thanks. So thank you for watching this video, and goodbye till we meet in the next lecture.